to do a very gentle introduction to this topic of machine processing of speech. Okay, all right. So with that note, let me get started. So what I'm going to do, I'm going to talk about a little bit of the problems that are involved in speech recognition. What is the current state of the art and so forth. And then I will talk about some signaling, modeling, and characterization. So some of you may have some signal processing, signal modeling background, signal characterization background. Many of you would be in product design and those aspects as well. But for some subset of you who have some interest and knowledge in signal processing, this may be a little bit more appealing. I mean, the second uh, bullet point here. Then we'll talk about how to take, the simple models and characterization of the signals that we will talk about, put it together to build something as complex as speech recognition and speaker recognition. So let us see what goes under the hood on all these things. All right. So what and why are we in this topic, right? Speech information processing. There is already a course by this name, and as many of you may be aware of, right? Speech has a signal. Speech um, as a commodity for interfacing with machines. Speech as a medium for interfacing with machines has picked up tremendously in the last 5 to 10 years, right? You will see products all over the space, starting from your smart speakers, your mobile phones, your tablets, laptops, pretty much all your electronic gadgets. Now you can start interfacing with speech. On top of it, now the new wave of technologies and algorithms, people want to be even more contactless, partly due to the pandemic and so forth. You still want to use a speech to control your TV. Now, we work with Samsung as one of our one of our projects here in my lab, and they want to not only build it just for TV, for the Samsung's microwaves, washing machines, your toasters, all pretty much all electrical devices that you can have, TVs, everything that you can have, your AC, all of these devices, they are going to embed with small microphones. So microphones don't impede too much onto your privacy. So they're going to impart microphones in all these devices, and you can now control all of them using speech. So let us look at what this.
The rate fell to 6% in November 1986 period.
So I just played to you an audio signal. So it was talking a little bit about some stock and stuff like that. That was the audio that you just heard. But on top of it, I'm pretty sure all of you try to understand a little bit about who is speaking. Even though I never told you to listen to that or never told you to listen to anything in particular, all of you heard this speech sound. Pradipta, can you confirm if the audio was also played?
Yes, I can heard a female
Yeah.
voice briefly.
Correct. So Pradipta now said something more than just the content. What Pradipta now said was that he heard a female voice. So not only are you trying to process what is the spoken content, you are also processing perhaps there is any noise or a background effect in the audio. You're paying attention to who is speaking, like in this case, the gender. You're certainly paying attention to the content because you also want to know what is being spoken. That's always, whenever you know the language, you know the words in the language, your primary job is always to understand what is being spoken. Then you may also have heard and found that the style, right? If you pay particular attention, then you might have felt that she was kind of reading it out. Okay? If you listen to it maybe one more time, you would make a lot of sense for sure, that you would understand that she is also trying to read. So multiple such factors are being deciphered from this audio signal when you pay attention to it. So this is where the challenge has been, and this is where all these years it has taken for us to come up with technologies on speech. The reason being, it's all a one-dimensional signal. My own voice that is coming out to you through the microphones, through your network, and then back to you through your headphones or speakers is a one-dimensional signal, but it embeds almost all these characteristics. If my kids outside make some noise, who is speaking, you are constantly listening, paying attention to my voice. What is the spoken content is perhaps the most important question that you have to understand when you listen to me. And then, of course, my style, maybe I'm giving it in the kind of a talk mode versus I'm reading it out of a script, or versus when I'm conversing with somebody else. Right? So all these information characteristics are embedded. Now, the job of the machine or any automatic system, what you people or what we people are doing pretty much seamlessly, like pick any one of these aspects or factors, as I call it here, we are able to decipher them very, very seamlessly. And now the job is to make machines comprehend this, right? So the challenge in machines is to separate the factors. We humans from a very young age, from about 2 to 3 years, studies have shown human babies itself, or human toddlers itself, are able to do this aspect of separating the factors in audio signal very, very nicely. Now, therefore, we want to equip machines with the same capability to as much as possible level. Right? So let me just see where the current state of the art is. So this basically is myself about last week when I was trying to put this talk together. I was taking some audio from the internet, downloaded it, and then of course I wanted this to work on the US English. So I downloaded an US English audio file somewhere in the internet. I now went and logged into IBM's Watson Analytics. So this is publicly available for small amounts of testing and so forth. You can also, if at the end of the talk you're also keen on it, you can certainly Google for IBM Watson speech to text, and you can play the game that I'm going to show in this video. Okay, so this is a screenshot video of me trying to play with the IBM Watson system using some audio file. So let's take a listen.
For wrongful death. Karen Howard, wife of a Philadelphia Eagles executive, has been charged with leaving the scene of the accident. The civil lawsuit charges Karen Howard with driving negligently.
Okay, so as you see here, this is a part of a radio recording that I took out. So this was something different from typically what the models are trained with. They are mostly trained with some other sets of conversational or read speech audio. So I just picked some, purposefully I picked a audio file from the internet from a radio broadcast. And what you see here is that the model kind of gets most of these. So what you see at the bottom, you might have seen already how the model is transcribing while the audio is playing. What you see here is the model already picks up the words mostly right, or gets the words mostly right. So the Karen Howard's wife, charged with the scene, leaving the scene of the accident, the civil lawsuit, all these things are pretty much right. Where it kind of has still trouble is that because of the lots of the background noise, you might have also heard that there was a lot of connection issues in the radio broadcast that caused some background noise. And this background noise caused the system to hypothesize that there are more than one speaker. Although we could, as humans, clearly feel that there was this one speaker in the recording, he was the one that was speaking throughout the conversation, the machine somehow hallucinates more than one talker. So some issues there, which including in our group and pretty much a lot of other groups as well, we are trying to address these problems in the current technology. Okay, but the speech transcription quality, if you take the pure text out here, then you might see that the systems are doing rather well. So with that note, right, let us see where we are at. So how did this evolve? Right? There's a brief history of how speech recognition itself as a field came down to what you have now in your gadgets and other uh, internet connected devices, right? So first thing, people almost were fascinated ever since, let us say, artificial intelligence uh, as an area of research and fascination and science came up. Speech recognition has been one of the core problems that has been identified as challenges to the artificial intelligence technology development groups, right? So speech recognition per se was felt as one of the holy grail tasks that one needs to show that machines can compete or outperform humans. So in that broad thought process, people started seeing that, okay, the speech recognition, a child, for example, gets 1 to 2 years of training to get himself or herself facilitated with the ability to process audio. Now the question is, since such a complex process is ongoing in the human child during its developmental stage to equip itself with speech and language knowledge, people started feeling that maybe it's a little hard task to achieve the capabilities of the humans right away. So they started simplifying the problem. First way to simplify the problem was reduce the number of words that are possible. So this is what is called a search space. So if you have the words of the language, if you have 5 words or 10 words, all you are going to look at is only among those 10 words. Say, for example, digits. So if I want to just have a system that takes a string of digits like 12845 and tries to predict the text for the audio that I just spoke, then all you're looking for is every time in a search space that is limited to 10. So what you see then is there are different, let us say, colors in this plot. On each plot, you also see some numbers written. So that is the number of words, that's the range of words that the system is expected to recognize. So, and the style of the words is what the color represents here. So if somebody is looking at a piece of text and reading it, they try to pronounce the words very clearly and they try to articulate it very nicely. So that means the red speech is the most high quality speech that one can generate. So people then started understanding or recognizing speech that was read and easier to do. So as you see over the years, almost everything gets better. So people started with 1,000 different words. That is what 1K means of read speech. That is in the late 80s. And that tasks progressed through mid 90s. Then people started feeling, hey, we are getting reasonably good performances here. Now, why don't I increase the complexity of the task by increasing more and more number of words in the search space? So 5,000 words, 20,000 words. And then when you also have noisy microphones versus clean microphones, people always felt that when you have noisy data, the performances were even worse. And what you see on the y-axis is the error rate. So word error rate is one of the common metrics used in speech recognition. The word error rate typically means what percentage of words in the model's prediction are not in agreement with the ground truth. All right. So then you kind of go into the next level of complexity, which is broadcast speech. That's what I show here in the blue color. And then people started improving that into the early 2000s. And then finally, the most, let us say, difficult domain or paradigm of speech recognition, which is conversational speech. So when you talk to your friends or parents or family or other people, you kind of assume a serious level of code. You assume a lot about the other person, and therefore you kind of mispronounce, sometimes even not complete sentences, but still make sense for the other person. So for these kind of audio signals or audio data, the systems have significant trouble because of the lack of structure or the reduced presence of structure. So conversational speech, although the research started very early, like mid-90s, but pretty much nobody really had any system that was useful up to say mid-2000s. And when about 2012 or so, the systems were pretty much before this deep learning era, they were around the 10% mark or 11% mark in terms of the conversational systems. But now in the last, say, 8 years, 9 years, with the advent of deep learning and those aspects, now we're talking about 5% word error rate. People have also done experiments with human subjects, how good they are in transcribing audio, and humans are about 97, 98% accurate. So about 2 to 3% error is what humans make in this task. So there has already been claims that we are getting close to human parity on these tasks, that machines are already as good as humans in listening and understanding audio of conversational nature. Huge claims, tall claims, but partly I don't subscribe to it fully, but as a product, right now it's ready to be, let us say, for mass consumption. So let's look a little bit under the hood. Pradipta, any questions up to this point that I should take?
I don't see any raised hand, so perhaps you may proceed.
Fine. Right. So feel free to, in my classes, lectures, anything, I always encourage everybody to participate. So please feel free to stop me, ask anything that is of context and relevance to what we are talking. So, use your raise hand button for signaling to me that you want to talk, right? Perfect. So then let's go down a little bit under the hood. So we kind of set the stage in the last 15 minutes or so, why speech recognition is challenging, what has been achieved over the years, and so forth. So speech as a signal, as we talked about, has a bunch of these characteristics that make it a little harder to process and to extract information out of. So I am just going to, in the next, say, 10 minutes or so, outline some of the state-of-the-art efforts into processing of speech. You could ask the question, is this the best way to do it, or are there gaps that one can address? Certainly there is certain scope for research in all of these, but we will just pick the template of the current system and then dissect it, right? What happens inside that? So the first thing is that you want to look at small windows of the audio. You don't want to take the audio as a full file and then trying to start making sense out of it, because the signal is very, very fast and time varying, because the signal content keeps changing all over the place. So to keep track of what is happening at short frames, instances of time, we need to look at short spans of the audio. So a common approach is to take about 25 milliseconds of audio. So this corresponds to a short window, is even lesser than one sound. Like when I make a sound like ah or something like that, that's already 100 milliseconds. It's already 10th of a second. So 25 milliseconds is even shorter than a full sound. So now what you do is you take the audio, and if you have some signal processing or other background, you can call it a spectral conversion. If you have not had any signal processing background, all you can assume is there is a transformation. There is on this window of the signal, you apply some transform that now splits the audio into a frequency space. So you see that the audio transformed on the short-term spectrum side that I'm calling, you will see that there is a variation of what is called the magnitude, meaning the strength of the audio, versus on the x-axis is the frequency. So this is some way to analyze signals that we use. Take the audio and convert it into a short-term spectra, and now what we kind of do is to analyze these spectra in some bands. So the entire spectra is very fine. We, from hearing studies, from knowledge of how the human hearing system works, we know that the human ear is very sensitive to low frequencies, like small tones, like your cycle's ring bell, right? The cycle's ring bell is around 500 to 1000 hertz. So when you see somebody ringing the bell of a bicycle, then that is of your most sensitive hearing part. The car horns, you may find the car horns and other horns outside very annoying. Why? Because this is in the region of your most highly sensitive auditory spectrum. So the 500 to 1000 hertz is where most of your human hearing is very sensitive to. So we also know that when you go for very high frequencies, like a shrill sounds, like, very, very fast changing sounds, like above 5000 or 6000 hertz, your auditory system is paying lesser and lesser attention to it. Right? The only thing that you will perceive as very high frequency is these beats. So you will see in music you have beats, but beats are not necessarily only high frequency. When you have a beat, it spans all the frequencies. So you get to hear the beat as something very, very fast changing. So the human auditory system has a particular way in which it analyzes the audio into different frequency components. So the current system still try to derive some knowledge out of this and exploit them in the system design. So take the audio, transform it into some frequency space, now split the space into certain chunks of audio called bands, and now on each band, you convert them, you kind of sum the energies in each band and get them into a single vector. So integrate them, you also apply a log compression. Why the log compression? Because again, the magnitudes are not what we are sensitive to. We are sensitive to log of the magnitudes. One common example that I can cite where log of magnitudes are already in play, when you actually pick up your TV or your mobile phone and increase the volume. When you press one button, it is actually increasing the magnitude in a logarithmic space. You are actually exponentially increasing in the magnitude of the audio, although the levels are in log level. So you perceive 1, 2, 3, 4, 5. So as the audio levels in your phone, let us say when you go from 2 to 3, you perceive that your audio has increased by some same percentage as when you go from 3 to 4, but apparently on the magnitude space, it's changing exponentially each time you increase the volume. Right? So log is done, and a discrete cosine transform is also done. I don't go into too much details of it, but all it does is basically to decorrelate the audio features to the same dimensional vector. You don't need to do the DCT. In fact, the modern systems do not even perform the discrete cosine transform. They just take the log of the magnitude of the spectrum, and that is what is used as the features. But what I just discussed now is a very famous and very, very popular feature extraction approach in audio world called the mel-frequency Cepstral coefficients, or the MFCCs. Okay, mel-frequency Cepstral coefficients, or MFCCs, are these features that are taking the audio and then converting it into short windows, and in each window you extract a vector. Now what do? We know how to do one window. Why don't we repeat it? We just take multiple windows across the course of the audio, and then voila, you get this sequence of vectors. Right? Now on top of this, we are, as we said, we will be taking the audio in multiple different environments. Like for example, you want to use your speech recognition engine in a car, on your cell phone. When you are doing a meeting, you want to do speech recognition on the meeting set. So what commonly happens is when the speech signal comes, there is some background noise, and there is also some channel. What do we mean by channel? Channel is everything that comes between your mouth and the microphone. So all these effects come into play, and these tend to corrupt the audio, which then goes into the automatic systems. So one common way to mitigate the effects of the noise and the channel is to assume some model of these. So I'm not going to go into details of how the modeling is done, but you could assume that there is something additive in the noise and there is something convolutive in the channel, and this is what comes into the system. So some linear effects are taken into account through these convolution style models. I'm just quickly going through it to say that, on the MFCC space, you can see that there is an unknown additive term that comes in that represents the effects of the channel. So what is commonly done is to now take the entire sequence of the MFCC features that we just discussed and remove the mean. The mean is somehow representative of the first order effects of the channel and the background that you are at, and you don't want to pay attention to that when you want to recognize speech. So it's commonly done in practice to remove some mean of these Cepstral coefficients that I just discussed. Okay, some detail, but that's what is done. And you could do more things, like you can perhaps do, some of you may be trained in statistics. You can look at, let us say, a sequence of these numbers that are coming in your MFCC features. You can see the distribution of those and map it to some target distribution. The assumption is that when you do this kind of histogram mapping, you kind of get some invariance to noise and other artifacts that are present in the audio. Okay, again, I'm skimming through it. I'm not going through the mathematical details. I do not know what is your background on all these topics, but these topics and the references are also given here. If you are more keen on it, you certainly can go through to the references. All you're doing is looking at a distribution of a set of data dimension, and on each dimension you try to map it to a target distribution. So this kind of is done. These processes of the last couple of slides have been to remove some impact of the noise, the channel characteristics, the background and ambience in which the speech is generated. You try to remove the mean, normalize the variance, or you might even go high more than that and say that I want to also have the distribution warp to a Gaussian style density. Okay, so multiple small steps which are low complexity, because you also want all these steps to sometimes even run on your edge device like your cell phone. So we do not want to have heavy compute or heavy processing even when we do some noise removal or noise suppression. Right, so simple steps to take your audio, convert to features like short windows, vectors out of each of these windows, now done gone through some mean and variance normalization. Now we have prepared the audio into a sequence of feature vectors. How do I do speech recognition from this? So the common way, or the state-of-the-art systems these days, how they do it is, so if you are given an input, as we said, on your left side, you see a set of vertical blocks. Each is supposedly a vector. The word that I'm saying at this point is the word one. Okay, the one in phonetics is what you see here. Wa, in, that's one. Okay, so the word one, when it got cut into 25 millisecond chunks and gotten processed with these features that I discussed, you get a sequence of these vectors. Now, for every vector in this, during training, you associate it with one class. Right? So you associate it with one phonetic sound. So the phonetic sound that you are associating it for the central frame is the sound right? In. So the second sound is what you are mapping to. The early part of the word, the vectors that come from it, we are mapping it to the sound wa, right? So wa, in. And the last part, you will be associating it to the sound in. So these classes are called the triphone classes or phoneme classes. And what you essentially do is to take your feature vectors and learn a mapping from the space of the features to the space of the sounds. The mapping is pretty much a classical machine learning problem. You have a set of input features. You have a set of target labels. Now I need to learn a classifier on the audio data that maps the features to the space of the classes. right? The phonemes are the common, let us say, output units. You can change it to syllables if you want. Certain languages like Chinese and Japanese, it's not phonemes that they use syllables. Even Indian languages, when you want to do speech recognition, you would use syllables or characters as the output sounds. For English, it's very common to use phonemes as the final target class. And what is the term triphone? The term triphone is used to also combine, or let us say color, each phoneme with its context. So you want to not only consider a phoneme as an individual entity, you want to consider the phoneme in the context of its neighbors. Like, in the context of wa and n is different from, let us say, in the context of, say, a and right? So different context, you want to color the classes differently. So essentially what you're saying is, I don't want to only consider the 30 or 40 phonemes, but I want to consider multiple variations of each phoneme due to the presence of different phonemes in the neighboring context. So some refinement of the target space, if you don't want to care about all those, you can just say that we are mapping audio features to speech phoneme classes. Okay, audio features to speech phoneme classes. So we use neural networks or deep learning aspects. This is how the modern day era of speech recognition works. So I don't know again how much of the background on deep learning and neural networks the audience has at this point. All I will do is walk you through some basics of this, so that even if you have not heard of it or come through it before, it's not a big deal. So what is happening in these models is called a multi-layer perceptron. This is essentially some work that came in the 80s itself. It does a bunch of transformations. So X is the input always. There are some layers of transformations. Each layer performs some affine transform, meaning it takes the input X, multiplies with the weight matrix, adds a bias, and then you perform some nonlinearity. And you keep repeating this over multiple layers till you get to some representation which can be mapped to the phoneme classes. So non-linear transformations of the audio that are, let us say, placed in a hierarchical fashion to map the audio into the corresponding classes of phonemes. Okay, and what are the unknowns in the system? What is a model then? The model is to find these weights and biases. So the model is these weights and biases are unknown, or they are randomly initialized, and now you have to go through an iterative process of training, meaning so-called changing the weights and bias, so that now they can do a better job of mapping the audio features to the phoneme classes. So here is a very intuitive example. Assume that you have only two classes of phonemes. Okay, let us say an R sound and an E sound. So the R sound here is represented on the right side color in red, and E sound is represented in blue. So when I walk you through the neural network, what you will see is that the representations undergo a series of transformations that make the audio more and more categorized, and eventually at the last layer, the classes separate out nicely. Now what happened is that I can simply draw a line and say that everything on one side of the line is the R class and the other side of the line is the E class. This is basically deep learning's prerogative to achieve, and I just gave a 3-minute or 5-minute summary of what the deep learning systems try to achieve. So hierarchically transform the audio, move it into a space where you can separate the sounds into the different phonemes, right? So going back to what we want to achieve, what we want to achieve is take the sequence of audio. You see the audio as a feature vector sequence that is on the total left of this block diagram. In the center is the deep neural network, and in the right is the output. So what is it that the neural network does? Every single vector on the left is converted into some output probability sequence. What is the output probability sequence? It is over the different phonemes in the language that are possible. So at every instance of time, you are asking what is the most probable phoneme that is present at the given time. Let us have a more zoomed out look or zoomed in look of the output, right? So this is what the model outputs generate. What is the y-axis? What is the x-axis? The y-axis is the set of sounds, a, o, au, and so forth. All the way up to the 40 speech sounds are lined up on the y-axis. On the x-axis is, of course, time, because you know that you have taken 25 millisecond chunks and you have proceeded through the audio by stacking all these features. Now, every such feature goes through the neural network and generates one vector of probabilities across the speech sounds. So when I move to the next vector, I get another sequence of probabilities or another vector of probabilities, another vector of probabilities. So what I'm showing you now is the entire sequence at the output level. So each time instance, you get only one vertical slice of the features that you are seeing on this 2D picture. So let us take an example, right? Let us take, if I take a 0.4 seconds, so if we can zoom in on the x-axis, 0.4 seconds, let us say there is an input feature vector that is coming in, and when that went through the model says the highest probability is for the sound ah, and the rest of the sounds have very low probability at that point. So this is what the model outputs. It outputs a posterior probability of a particular class given the input feature at that time instant. So what you see, the dark red colors means very high probability for that particular sound. If there are more than one classes that are competing to claim for a given region of audio, then you see confusions. So in an ideal world, you would only see, when the model does its job very well, you will only see ones and zeros in this output. But the model is not ideal. The data is perhaps a little noisy also in this example that I picked. So you see some confusions present in here. But the whole task now has been to convert your sequence of MFCC features into this posterior probability space. Then all that is left is put some constraints in the posterior probability space through language models. What do we mean by a language model? This comes from natural language processing and text processing. We know that certain sounds are more likely to follow certain other sounds. There is some structure, there is some grammar, there is some way of pronunciation. So we enforce these structures on the outputs of the posterior probabilities, and out comes the text. That's all that is done, right? So audio features, neural networks, output of the neural networks being post-processed with some structural models like the language models, which enforce some pattern or structure in which the sounds can come, right? So then, you know, these outputs become the so-called text that you generate out of the speech recognition engine. Right, so let me just quickly take you through what the neural networks do. Is basically one a paper has basically dissected it for audio. I won't take you through all the details. All I will try to say is that in the early layers, so different colors here, for example, correspond to different speakers in this plot. This is a two-dimensional pattern of the speech processed through a neural network, and each person is saying the same content. Everybody is saying, you know, something like, my car went for a wash yesterday and it became clean. So some sentence of this nature everybody is saying, and we are looking at the speech recognition neural networks, different layers, and each color corresponds to different speakers. So as you walk through the neural network from the first layer to the second layer, and when you get to pretty much the seventh layer, what is happening is that the colors start coming together. So colors coming together means different speakers speaking the same content are aligning. So the variability of my speech versus Pratita's speech or your speech is getting normalized in the neural network. This is the key task that the neural network is doing. It's trying to invariably map multiple voices to the same space of speech sounds. Because the moment I want to convert to text, my voice text and Pratipta's voice text are exactly the same if we say the same thing. So somebody has, or the model's job is to normalize this variation, and that is exactly what the neural networks do. In another study, people have found that for speech sound properties, each layer of the neural network has increasingly better speech sound characterization property. This is what you see on the left. And when you look at some speaker characteristics, let us say I want to design a gender classifier. And if I take the layer 1 output, layer 2 output, layer 3 output, and design a simple gender classifier, you see that the gender classifier has a decreasing performance. What does that mean? The neural network improves the speech content factors as you go from layer 1 to 5, and it suppresses the speaker factors like the gender factor as you go from layer 1 to 5. Right? So if you remember the first motivation I gave, I was trying to say that the key challenge is to remove aspects of the speaker and other aspects and enhance the aspects of the content or the phonetic sounds. So this is precisely what the deep learning models are able to achieve. Okay, just I will spend 5 more minutes on a completely different task that's also becoming very seriously commercially viable, is now to move to the other task. Like now change the problem. I don't want to understand what is being spoken. I want to understand who is speaking. Where is it commonly used? Where do you want it to be used? Now, more and more of security, biometrics, and banking systems want to use speech as a modality to authenticate users. Right? You want to use, you pick up your phone or your laptop and you just say, something like a passphrase, and the system will say, yes, you are the person, or no, you are not. So this Microsoft
My
system.
voice is my passport. Verify me.
So I'm testing a Microsoft system, which is already out there, which does it.
My voice is my passport. Verify me. My voice is my passport. Verify me.
So what I did just now was enroll myself into the system. I need to say something.
My voice is my passport. Verify me.
Enroll. And now I'm checking whether the system accepts me or not.
My voice is my passport. Verify me.
So I try to change my voice to see if the system does it. This was still me speaking. I tried to change my voice as much as possible to sound differently. And now I can say that the system also rejected me. So there are 2 stages. All I wanted to convey with this video was, in the first stage, you give 3 recordings for the system to understand that this is me. This is like you setting your password twice. In your text-based mode, you will test set your password, and then you confirm your password, and that is set. Right? So that is what I did in the first phase. I gave 3 recordings of my voice, and the system kind of accepted me as the user. Now I'm going into the system later and giving another recording and asking the system, will you verify whether it is me or not? The first time it verified, but the second time I changed my voice quite a bit, as you heard, and the system rejected. Right? This is just an example of already a Microsoft Azure system that does speaker recognition. So what goes under the hood? It's pretty much the MFCC features that we discussed, but you do completely different statistical models. You do different models to summarize the audio. All you want is, you don't want to look at the fine print of the audio. We want to summarize the audio in a statistical model, and then you want to say that the summary of this audio recording and summary of that audio recording, do they match? Right? All you're doing is you take the audio features, as I said, summarize the audio in some model space and get a embedding vector that is shown here. And let us say when somebody else tries to verify it, that audio portion is also summarized into another vector, and then you simply measure some glorified distance. And if the distance between the 2 vectors is above some threshold, then you say, hey, this is a completely different speaker. The distance is below the threshold, then you say yes, this is the same speaker and I want to accept it, and the verification is accepted. Right? This is how this technology works. Okay. I'm sorry I can't go too much into details of all these systems due to the scope and lack of time, but this is just, say, let us say, an introduction or a gentle introduction to this system. So when you do things like text dependent, when you force that everybody has to say the same thing, right? Where the state of the art here, the state of the art can achieve less than 1% error for speaker recognition, which is why now banks, last month I was in Delhi for a meeting with UIDAI, which is your Aadhaar. So Aadhaar is also now keenly interested in using voice as a method to enter the biometrics of users. So question then, before we leave this talk, I want to ask, have we solved the problem? I mean, I kind of talked about a bunch of success stories where it is working and so forth. So I want to leave you with where are the unsolved problems in this space and what we as a group in our research and all that we are trying to do. So prior research focused primarily on single speakers recorded in single microphone. But this has been the advance that has been made. The moment you pick your phone and you talk to the system, you are the only person talking to the system, and there is only a single channel of communication between you and the system.
The basic word important system.
So let me just play an example of a meeting conversation and how the system responds to this speech recognition engine.
The basic word important is offline as well. The combined measure might not be if we want to wait what the user has typed into the message.
Okay. Mine's going to be mostly using the offline, but the actual stuff it's doing will be online. It won't be very processor intensive or memory intensive.
So there's some conversation about a system building that I picked, and there are at least 3 speakers in there. They are far from the microphone. There is some background noise and effect due to this. So if I pass these systems through the state-of-the-art speech engine, what you see is the reference on the left, which started with something like basic word of importance is offline as well, and combined measure and so forth. This is the left, but you see what is happening in the output of the speech recognition engine. It kind of gives up on such recordings. It kind of is not able to do a reasonable job. So in these settings, when multiple speakers are present far away from the microphone and they are talking to the system, you have research challenges. You get 30%, 40% word error rate, or sometimes even beyond that, and make them completely non-usable in a commercial setting. So this is where we have projects also with different customers and people in conversational audio. For example, one project that myself and Pradeepta are all involved in is a project with British Telecom, where they want to automate customer agent conversations. So when multiple speakers are speaking and they are conversing in a freestyle, speech recognition engines are not able to.
The basic word importance is offline.
Just playing it again.
The combined measure might not be if we want to wait what the user has typed into the message.
Okay. Mine's going to be mostly using the offline, but the actual stuff it's doing will be online. It won't be very processor intensive or memory intensive.
So what you see is that it has completely not gotten much of the spoken content. So that is what we also worked on in the recent in some workshops on diarization and speech recognition in the wild. Yeah. So pretty much I'm also getting close to the top of the hour. So I would like to thank you for your presence. I would also like to apologize for me not able to take this talk last week due to some family issues, emergency health issues that happened. And I'm glad that we could schedule it again and get this done. Thank you, Pradeepta, for also inviting me and hosting me in this